Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Assalamu alaikum wa rahmatullah. Welcome to the first lecture of our week 4, and we were discussing chapter number 11, metal casting processes, in the last week, and almost we have done with almost all the types of the casting process, but you are supposed to study two topics by yourself. The first one is section 11.4.2, and that is even of cleaning and trimming and pouring, that section, and 11.5, that is casting quality, and 11.7, that is design consideration. And should you have any question, you may contact me. And these are only, like, you can say, half page topic, and it's also a half page, and so do this one. So they are not a very lengthy topic, they are only half page each. So now, in this week we are going to discuss second domain of our subject, that was the deformation process or the metal forming, and so we are starting CLO2 of our subject. So in this CLO we are going to start with chapter number 18, that is the fundamentals of metal forming. So let's start with it. So what is metal forming? Metal forming process, it is also known as the deformation process. It is also known as the deformation process. So the metal forming process is basically the kind of the manufacturing process in which shape change is achieved by plastic deformation by applying the stresses. In the previous chapter we were discussing the shape change by the application of temperature. So we have the processing operation in which we are achieving the shaping process, and in those shaping process there were two methods which attaining shape change by temperature, or you can say by melting, and we have discussed the casting in this domain. The second method for attaining the shape change is by plastic deformation. Or by applying the stresses, okay, or forces. So our second domain is the metal forming process or the deformation process, in which we achieve the shape change by application of stress or by the plastic deformation. So that is why it is also known as the deformation process. In this kind of shaping process, the stress that are applied mostly are compressive in nature, while in some cases we have tensile stresses. In some cases tensile stress are also. Okay. So what kind of materials are subjected to metal forming or the deformation process? They are mostly a highly ductile material and having lower yield strength. Highly ductile so that they don't fracture during the deformation. If the material is brittle, as you know, that it will not undergo plastic deformation, rather it will fracture. And lower yield strength so that it is easy for us to change the shape. This is the first thing. Second thing, we can perform the metal forming operations either as a cold working operation or the hot working or the warm working, and we will see this in the slides ahead, what is the difference between these three. So if we see the metal forming process, these metal forming process can further classified into two types. The first one is termed as a bulk deformation. If I write a name here as well, it's a deformation process. So the deformation process can further be classified into bulk deformation and the sheet metal working, and there are further types. So what is the bulk deformation? A deformation that is being produced in a bulk material, a deformation that is being produced in a sheet. So sheet metal. So what's the difference between bulk and sheet metal? The bulk, a material with low surface area to volume ratio, while the sheet metal is a material with a high surface area to volume ratio. What does it mean? Let's suppose you have a steel ingot. You know what the ingot is, a large bulk material in the simple shapes. So that is 2 meter on each side. Let's suppose that is 2 meter on each side. So it will have a volume of 8 meter cube. But we have another thing that has let's say 8 meter cube. Okay, then we have another sheet like, let's suppose it is 2 meter on this side, 4 meter on this side, and 1 on this. So again we have 8 meter cube volume, but we know that we have the greater surface area here compared to the surface area in this one. So we can say what it has a greater surface area. So this is the difference between the bulk and the sheet metal. The bulk has a lesser surface area for the same volume, while the sheet metal will have the greater surface area for the same volume, although there are some restriction how thick the sheet can be, and we will see when we will specifically discuss the sheet metal processes. Okay, so what we have seen that the deformation process or the metal forming process can be further classified into the bulk deformation and the sheet metal working. And what is the difference between the bulk and the sheet metal? The bulk, which has the lower surface area to volume ratio, has a lower value, while in the sheet metal the surface area to volume ratio has a higher value. Now if we have referred to this chart again and again during our lectures, we started here in the first lecture. We were discussing manufacturing processes. In the processing operation, we discussed that there are three processes in the processing operation section. The first one where we shape the part, and in the shaping we discussed there are two ways to shape the part. Either we melt the material and pour it into the mold and allow it to solidify in the specific shape. That process is termed as the solidification processes. And in the chapter 10 and 11 we discussed those processes as a casting of metals, then further classification of the casting. Now we are moving toward the second type, that is the deformation process, which has further bulk deformation and the sheet metal, and each of these two has its further classification. So this is now we are moving towards, we will be discussing the bulk deformation as well as the sheet metal operations. So I hope you keep track of this chart. It will help you to summarize your subject in a single chart and help you to remember the classification or the interconnection between all the processes. So starting with the first type of metal forming or the deformation process, that is the bulk deformation. We have discussed what is the bulk deformation, in which the deformation is produced on a bulk material, and what is bulk material, which has lower surface area to volume ratio. So that is one aspect. The other aspect is they are used where significant deformation and massive shape change is desired. So beside this, there is another quality of this bulk deformation, that is where we desire significant deformation and a massive shape change. In the sheet metal operation, there is not significant deformation or the shape change, unlike the bulk deformation. So what are the types of the bulk deformation process? We have the rolling, forging, extrusion, and wire and bar drawing. And if you remember, we just quoted in the first slide that in the deformation process, the mostly we apply the compressive stress. So if you see the types of this bulk deformation processes, among these four, three of them are applying the compressive stresses. The primary driving force is the compressive stress, while the last one, wire drawing, it is applying the tensile one onto the work part. So there is tensile involved, but in rare cases, in a few cases. So in the build deformations, the starting material may be cylindrical billets, rectangular bars. It can be ingots, as we have discussed earlier. So this is the rolling operation in which metal is squeezed between these two opposite rolls. And we have the forging one. We have the two dies, and metal is compressed between these two dies. And we have the extrusion one, in which a metal is forced to squeeze out of a die opening. This is the die opening, and metal is forced to squeeze out of the die opening, taking the shape of the die. Or we have the drawing, in which metal is pulled out of a die opening. Okay, and we will discuss one by one in the next chapter. In this chapter, we will be discussing some basics of all these processes. So, what is the rolling? It is extract from your book, course book. So, what is rolling? There's a compressive deformation process, as we discussed before. It's a compressive deformation process in which thickness of a slab or a plate is reduced by two opposing cylindrical roll or the tools. So we have the two opposite cylindrical rolls here, and the thickness of the slab is being reduced by compressive stresses. The roll rotates so as to draw the work into the gap between them and squeeze it. So there is no other force involved. These roll themselves, so take the part into this gap, forces the part into this gap, and compress it. So they are utilizing the frictional force to push the part into this gap, and then they are applying the compressive stresses onto the part to reduce the thickness. The second one is the forging one. In this kind of the deformation process, as we discussed, the work part is forced or is compressed between the two opposing dies. So we have the lower die, a part is placed over it, and then we have the upper die which is applying the stress. This one is stationary in most cases, other one is movable. Okay, and this is our work part. This is the work part. So this is how we perform the forging operation. Again, all of these four processes can be performed as the cold working, hot working, or the warm working. Then you have the extrusion one. As we have discussed, it's again a compression process in which the work part is forced to flow through a die opening, and ultimately taking the shape of the die. So a metal is forced, this is the metal that is forced through the die opening, taking the shape of the die. And the last one is the drawing one. It's a forming process, and the diameter of round wire or the bar is reduced. So the primary purpose of the drawing operation in the ball deformation is to reduce the diameter of the wires, the much smaller diameter, and the bars comparatively larger diameter. So they are pulled out of a die opening to reduce the diameter. So this is some basic about the rolling and the forging. Then the sheet metal, the second branch of the deformation process, we discussed. They are used where there is no involvement of the significant shape change. So they are the metal forming process and the cutting operation of sheets, coils, or the strips. So you can see there is not that much significant shape change or the plastic deformation involved, but they are involved with some smaller amount of deformation and some cutting operations. The sheet metal working operation, it is also known as the press working. Okay. Hydraulic presses are mostly used for performing these operations, so that's why they are also known as a press working. And the product obtained from this sheet metal, it is known as a stamping. So I can call this one as a stamping, or this angle iron is a stamping. Okay, so the product of the sheet metal operation is termed as a stamping. As there is no significant shape change involved, so the sheet metal operations are mostly performed as a cold working process, because they are mostly the finishing processes in the deformation process. So that's why they are mostly performed as a cold working process, and cold working processing has some advantages, like it increases the strength of the material, and we will discuss it how. So that is why sheet metal working operations are mostly performed as a cold working. So they are performed by the tools. A positive part, it is known as a punch. The movable part, it is known as a punch, and the stationary part, the negative, you can see the negative part here, that is known as a die. So this one is a die, this one is a punch. So this one is the die, and this positive part, that is a punch. While in some cases there are some other features involved, and we will discuss all of these in the next chapter. Now here comes the stress strain curve. So what is a stress strain curve? It shows a relationship between the change in the behavior of the material or the deformation of the material with respect to the applied stresses, right? So we know there are two behaviors of the material: elastic behavior and the plastic behavior. There are two behaviors or the two deformation in the material. Elastic behavior, in which once the force is removed, material will regain its shape, right? Elastic behavior is one in which once the force is removed, it will regain its shape, while in the plastic one, it's a permanent deformation in which even if the force is removed, it will not regain its original shape. That means it is permanently deformed, or the permanent deformation, or the plastic deformation. So you must have seen that in the elastic region, the stress the stress is directly proportional to the strain. That is the Hooke's law, right? So if we start here, the stress will be directly proportional to the strain, and once this stress is no more directly proportional to the strain, there will be a beginning of the plastic deformation, and that point is known as the yield point. That point from where the plastic deformation starts, that is known as the yield point. Means beyond this the yielding starts. So this strength, the stress value at that point, is known as the yield strength of the material. Okay, then there's a beginning of the plastic deformation. So and in the plastic region, that stress is no more directly proportional to the strain. As you can see here, with the small amount of the stress applied, there is a larger amount of strain that is being produced. Then you can see here, with this amount of small value of a stress, there is a greater strain produced on the x-axis, right? So it means there is some different relationship between the stress and strain in this region. So the region before this yield point, that is known as the elastic region. This region is known as the elastic region, as it's seen here, and the region beyond that is the plastic region, right? So once we start to deform the material with the plastic region, its strength will increase for a moment of time. And why is that so? Because of a thing called a strain hardening. As you can see here, after the elastic region, we require more amount of stress value to cause little amount of strain, right? And that is because of the phenomenon that's called a strain hardening. What is the strain hardening? If you see a metallic material, let's suppose, under the microscope, as you discussed, there are regions within the material, and in each region, atoms are arranged in specific order. Atoms are arranged in the specific order in each region. Each of this region is known as a grain. We have discussed briefly this grain before, earlier, in the casting chapters, fundamental of metal casting. So if you see a metallic material under the microscope, it has regions on it, and in each region atoms are arranged in a specific order. And if you see, the electric poles on the street, and if you go if you see it closely, observe it closely, you will see some patches over that metallic pole. You will see some bright or the dull patches. So these patches are These patches are basically the grains that are visible. So once such material is under the stress and you apply the force that's under the stress, there is a sliding occurs onto the layers of atom. So if you see each grain, I am just enlarging this grain. If you see each grain, the atoms that are arranged here, they will start to slide over each other, and this sliding will continue until these layers reach the grain boundary. And because on the other side of the grain boundary, the arrangement of atom is different. Now atoms are arranged in some other pattern like this one. This is some other grain, let's suppose. So this movement of the layers of atom is restricted by the change in the arrangement of atom in the other grain, as there is a natural wall created because of the change in the arrangement of atoms. So this change in arrangement restricts the movement of material. So to break this resistance, we need to apply some extra force so that the deformation will continue. So this is called a strain hardening, because the material is getting hard and we need to apply extra force because of the strain produced. So this is called a strain hardening, the increase in the strength of the material due to the strain. So that's why once the material enter into plastic region, once the deformation start, so the grains, the atoms will slide over each other and ultimately they will reach the grain boundaries. In the other grains, the atoms are arranged in some other order, and it is providing resistance to the sliding of atoms. So the strain hardening occurs. That's why we see a sharp increase in the stress required to produce the strain. But that even occurs at up to certain point, that is known as the ultimate tensile strength. The maximum amount of stress that a material require for the deformation, that is known as the ultimate tensile strength. Beyond this ultimate tensile strength, there is a formation of the material starts to move towards a fracture. So if we are applying a pressure onto this material, applying the stress onto this material, so there will be a elongation due to the stress. Material will further elongate due to this stress, and after this UTS, ultimate tensile strength point, there will be a formation of neck. There will be a formation of neck here. Means the material is going to fracture, and this neck will further concentrate onto a single point, and ultimately we will have a fracture region. And this is called a fracture point. So this region is termed as a necking. This is the elastic region. This is the plastic region with a strain hardening. Okay, that's all for this stress strain curve. So there are obviously some terms that are involved with this stress strain curve. We have discussed what the elastic region is, where the material can regain its shape once the force is removed. Material is exhibiting the elastic behavior. And the plastic region, where the deformation is permanent, it will not regain its shape once the force is removed. We have discussed what the yield strength is, the maximum amount of strength that material have in the elastic region. Beyond this, there will be a yielding, a permanent deformation. And the ultimate tensile strength, the maximum amount of stress the material can bear. Beyond this, the fracture will start, and necking and the fracture. Although there are some other terms that are required to be discussed, that's such engineering stress or the true stress. There are two different things: a flow stress and the average flow stress. So we will discuss these terms now. So now we are moving towards these terminologies. The first one is the engineering stress. So as we see in this curve, that the force is being applied on the body and it is experiencing some strain, and ultimately it fractures. So if you see, let's suppose we have a specimen for the tensile testing. It has a gauge length of initial gauge length of L0 and initial cross sectional area of A naught, right? And when the force is applied on it, it elongates, so the gauge length changes, as you can see it is moving towards a fracture from here. So now the new gauge length for this specimen is L, while the cross-sectional area at this region is, you can say, A. The cross-sectional area will be A, right? So what is the engineering stress here? Stress is simply force per unit area. So which area is this one? This one or this one? So the engineering stress is the force applied per unit cross-section area. So that is the initial area, the original area of the specimen, or whatever the material we are applying the force. But as we know, once the force is being applied, so during this up to the fracture point, the cross-section area of the material changes. So the stress that is calculated based on the instantaneous cross-sectional area, that is termed as a true stress. So the true stress you can write it like force upon the instantaneous area. Just write that is force divided by instantaneous area. So if we observe it in the graph, so let's suppose this is the strain, this is the stress. So for engineering stress, it would be like somewhat like this one. We have a elastic region, then we have the plastic region. But there's a possibility that for the true stress we have somewhat different value, that it might go in the elastic region, then in the plastic region it will further increase, especially after this strain hardening. After this strain hardening point, or the UTS as we saw in the last slide, it will further increase. Why is that so? Because the cross-sectional area starts to reduce, so ultimately and the force applied is constant while the area is being reduced, so the true stress increases further. So the stress that is calculated based on the instantaneous area, that is termed as a true stress. So what is the relationship between these two? As we know that true stress equal to force divided by instantaneous area, but obviously the volume remains constant, so we can say by the constancy of volume, it would be V equals to initial area into the initial length, A naught dot L naught equals to instantaneous area and instantaneous length, that call it Li, right? So from this we can obtain, we know that true stress equals to force divided by instantaneous area, and obviously we cannot always observe the area at every instant, so we can simply convert it into using this one. So from here our instantaneous area would be equals to initial into dot divided by instantaneous length, right? So it can be written as F divided by A naught into L naught divided by Li, or right. But as we know, the strain is equals to L minus L naught divided by L naught, Li minus L naught divided by L naught, the length at any instant divided by L naught divided by L naught minus L naught divided by L naught. Okay, so we can write it as Li by L naught minus 1. So we have the true strain value as F by A naught into 1 plus epsilon, or the strain, or we can simply write it as true strain, or we can write it as true strain equals to engineering strain into 1 plus engineering stress into 1 plus strain. So this is how we can calculate the true strain, true stress, that is the so this is how we can calculate the true stress. Now for the true strain value, the true strain would be equals to, as we know, strain is the change in length divided by the original length. So we have change in length divided by original length from L naught initial length to L, just say, or the Li you can say. So using the integral for this one, because you're calculating for the total strain, so that would be equals to ln of Li by L naught, or we can write it as Li equals to 1 plus engineering strain into the L naught, right? So we can simply write it for the true strain, that is ln of 1 plus, let's write it correctly, this is a true strain value. So from here we can see that the true strain relies on the instantaneous area, while the engineering strain relies on the original area of the specimen. So that's why after the strain hardening, when the cross-sectional area starts to reduce, or when the necking begins, the true stress value keeps on increasing, while the true engineering strain value starts to reduce. So we have, until now we have discussed two terms, that is the engineering stress and the true stress. Now we'll move towards the flow stress and the average flow stress. So what is the flow stress? In plastic region, stress is no longer directly proportional to the strain, as we have discussed in the previous graph. Just draw a brief rough sketch of the stress strain curve. We have the strain here, we have the stress here, and we have the elastic region, then the yield point, lower yield point, UTS, and the necking, and this is the fracture point. This is a UTS, and this is the yield point, and we have the elastic region, and this will be the plastic region, right? And this is the elastic region. So in the elastic region, we know it follows the Hooke's law that the stress is directly proportional to the strain, but that's not the case in the plastic region. Stress is not directly proportional to the strain, rather it is exponentially proportional to the strain. So we have stress equals to directly proportional to the strain exponent n, or we can write it as K strain into n, where this K is a strength coefficient and the n, this n is the strain hardening coefficient. So if material is more strain hardened, then its value will increase. But one thing we need to remember, that stress and strain are the values of true stress and strain. So these stress and strain are the value of true stress and true strain. They are not the engineering stress or the engineering strain. Why is that so? Because we consider the flow stress in the plastic region, and that's why in the plastic region there's a shape change at every instant. That's why we consider the true stress and true strain. This flow curve was developed to define metal plastic behavior in cold working. Now, what is flow stress itself? So as we know, we define the engineering stress as the force per unit original area. We define the true stress as force per unit instantaneous area of the material. But what is the flow stress? It is defined as the instantaneous value of stress. Instantaneous value of stress. Why is that so? Because we are considering the true stress. So it's an instantaneous value of stress required to continue the deformation of the material. So the stress required to keep the material flowing, or the stress required to continue the plastic deformation, that is termed as the flow stress. So as seen on the stress strain curve, the strength of the material increases due to strain hardening. We have seen here the strain increases due to the strain hardening, so the stress required to continue deformation also increases. So once material enters into the plastic region, so as soon as the material starts to deform, the strain hardening will increase up to a certain point. So up to that point the flow stress will also increase, and once this limit passes, the flow stress will also reduce, right? So the common formula, you can represent the flow stress as YF. So these are the same thing. It is represented as a YF equals to K, that is the strength coefficient, into the true strain exponent n, that is the strain hardening coefficient. Then there's another term that is called average flow stress. As we know, we have multiple kind of deformation. Let's suppose we are performing the rolling operation or the forging operation. So let's suppose this is the slab, and there is a punch, and this is the die, and that punch is applying pressure onto this material, and it is applying a gradual uniform pressure. It is not applying the impact. So obviously for this gradual pressure there will be a deformation in a gradual pattern, right? For that one we consider the average flow stress, right? But if the load is kind of impact nature, we won't consider the average one, rather we consider the instantaneous stress, right? So it is just basically we have original flow stress, that is YF flow stress equals to strength coefficient into the strain exponent. So we have integrated this from zero strain hardening to the maximum strain hardening. So we got YF equals to divided by 1 plus n. So this is simply an integral of this one. So this is how we get this average flow stress. So it is average flow stress from the beginning of a strain to the maximum value that occurs during deformation. So the strain value here is the maximum strain value during deformation process. So the strain value it will take here is the maximum value during the deformation process, that is, you can say, towards the end of the process. What will be the maximum strain value in this case? When the material is in this shape, like this one, it has been deformed completely, now it has been reduced to this one, and we have achieved our final. So this will be the maximum strain of this material, right? So what is the difference between these two stress? Both are the flow stress. And what is the flow stress? The stress that is required to continue the plastic deformation. Now the deformation can be occurred in two ways. Either we are applying the impact loading, a loading that is applied for an instant, or loading that is being applied gradually, a gradual uniform or streamlined deformation that is taking place. So if the loading is impact loading, then we consider this flow stress, that is an instantaneous flow stress. Or if the deformation is in a pattern of gradual pressure, like in the case of the forging or in the case of extrusion in some cases, or the wire and the bar drawing, we take the average flow stress. So I hope you are clear with the flow stresses and the difference between the engineering and the true stress and strains. Now, as we discussed in the beginning, that the metal forming or the deformation process, I'm writing it again so that you remember that they both are same, they both are, you can say, synonyms. So the metal forming process or deformation process are of four types: rolling, forging, extrusion, and the wire and the bar drawing, right? And these four processes can be performed in three ways. The first one is called hot working, or you can perform these four types of deformation process as the cold working or the warm working, right? So all of these three processes can be performed as in these three conditions. So what is the cold working and why it is used, why it is preferred? So what is the cold working? A metal forming process performed at a room temperature. So we are not our specimen is at the room temperature, it is not in the heated form, or if it is heated, it is slightly above the room temperature, like it's not a very hot or even near the recrystallization temperature. It is far away from the recrystallization temperature. So that is termed as a cold working. If our specimen or the material is at the room temperature, then that is termed as a cold working process. So why the cold working processes are preferred? What are the advantages? The main purpose of the cold working operation are, as we discussed, when the stresses are applied, as I told you before, there are grains inside the material. Each grain has different arrangement of atoms within it, right? And so when we apply the stresses, these atoms start to slide, the layers of atoms start to slide over each other until they reach the grain boundaries. They strike with the layer of atoms in the other grains, which is oriented in some other pattern. So that create a barrier for the sliding atoms. So that sliding atom produces the strain hardening. So in cold working processes, strain hardening increases, the strength of the material increases. And why the strength of the material increases? Because of the strain hardening. So cold working operations, either rolling in the cold working or the forging or the extrusion or the wire and the bar drawing, if they are performed as a cold work, it means our purpose is not to change the shape significantly, rather our purpose is to increase the strength of the material. The shape change is not our primary purpose, although there might be a shape change in a slight order, but the main purpose is to increase the strength of the material. This is the main purpose of the cold working. Some side effects of this one is that it has a good dimensional accuracy. We ultimately get the good surface finish. It has an isotropic behavior. There are two kinds of behavior in the metallic materials. So the first one is called as the isotropic behavior, and other one is anisotropic behavior. It means, you can say, uniform in all directions, while it is directional. What does it mean? Let's say if we have this specimen and I say it's an isotropic material, it means if I measure its tensile strength or compressive strength or whatever, in this direction or in this direction, it will give the same value. Means material is behaving same in these directions, in all the directions, while anisotropic material will behave differently in different direction. It might have some value of tensile strength or compressive strength in this direction horizontally, or it might have some different value in the vertical in this direction. So that is the anisotropic behavior. And because of this cold working, our grains are, let's suppose this was the original grain when it was cold worked. Now this is my specimen after the rolling operation, and this grain has been changed, like elongated. This grain has been elongated like this one. Now the layer of atoms is lengthier, is longer than before. So it means atoms have more space to slide when they are subjected to force, while atoms have lesser space than before in this direction to slide over each other. It means atom will deform less in this direction, while atom will be able to, this material will be able to deform more in this horizontal direction. So it means it is generating the anisotropic, it is behaving anisotropically. So the cold working operation give rise to the anisotropic behavior in the material. Then the last one is it obviously save the furnace and the fuel cost, because there is no requirement of heating the material, so we save the furnace cost. Now what are the disadvantages for this one? Obviously material is not heated, because heated material is softer compared to the cold material, so that's why the cold material is harder, has high strength. As we have seen, it has a strain hardening which increases strength. So because of this we need to exert higher force and power. So there's a requirement of higher force and power during these processes of body deformation. Work surface must be clean from the dirt. There's a chance that might stick to the surface, so it is a requirement that work surfaces must be clean before the cold working operations. And then the last one, the strain hardening limits the deformation that can be done. So obviously, as I said before, in the cold working operation, the deformation is not our primary concern. Rather, our primary concern is increasing the strength of the material. Although deformation is also taken into account, but it is not our primary objective. Our primary objective is the increase in strength. So the strain hardening or increase in strength limits the deformation that can be done. So if you have understood this cold working properly, it won't be difficult for you to understand the other one, that is a hot working. So what is hot working? In cold working, our specimen or the work part was at the room temperature or slightly above, while in the case of the hot working, the work part of the specimen is at least at the temperature of 50% of its melting point to 75% of its melting point. Let's suppose if a material is melting at 100 degrees centigrade, so for hot working of that material, it should have temperature between 50 degrees centigrade to 75 degrees centigrade, right? We don't exceed beyond this limit. Why is that so? Because when we deform the material, there's a heat generation in the deformation as well. There's a heat generation involved in the deformation as well. So if we heat the material at 75% of the melting point, plus there's a heat generation to deformation, so there's a possibility that material might reach to a melting point temperature and it will start to melt. So that is not our objective. So that is why we heat it from 50 degrees centigrade, 50% of its melting point, to the 75% of the melting point. And why do we heat it to a so high temperature? To achieve the recrystallization temperature. So what is the recrystallization temperature? Again, I've told you that in the material we have grains or the crystals which have some specific order of atoms in it, right? So when we heat the material up to a certain temperature, we provide enough energy to those atoms that they break away from these bondings and they can rearrange themselves. We provide them enough energy so that they can rearrange themselves, so that we can deform them in whatever manner we like. We don't have to exert much force to overcome the strain hardening. That is the purpose of heating to a recrystallization temperature. So in the cold working, we said our primary objective was increasing the strength, while in the hot working our primary objective is deformation of the material or to change the shape of the material. And how do we achieve the shape change? By heating it to a temperature of 50 to 75% of its melting point, or above the, you can say above the recrystallization temperature, so that material can be recrystallized. So what are the advantages of hot working? The first one, as we have already discussed, the shape changes involved. We can significantly change the shape of the material because the material is heated, so it is softer. It is at above the recrystallization temperature. There's less bonding between the atoms, so there's low force required for the deformation, while in the cold working we required higher force because it was strain hardened. That's why there's a possibility that metal might fracture in the cold working. A material which is brittle in nature, so if it is cold work there's a possibility it will fracture, so such materials can be hot work. Material which have brittleness in their nature, they can be hot work easily, but they cannot be cold work. The properties which we achieve in the hot working is generally isotropic, because we provide them enough time to recrystallize, rearrange themselves, especially when they are left in open air and allowed, or within the furnace to allow to cool down over the time. So they generate isotropic behavior. The atoms are arranged evenly in the material. Some common disadvantages for these are, we have the poor surface finish because there's a heating of the material involved, and there's a possibility that the oxidation occurs at the surface, so that's why they have the poor surface. We have high energy requirement for the furnace because we need to heat the material to such high temperature. Obviously for the metals or the steels it ranges in several hundred degrees centigrade. The last one is that let's suppose you are performing rolling or the forging or the extrusion, so the tool life which is the tool which is deforming the material, because of high temperature of work part, its life also reduces. Now this is one of the disadvantage of the hot working, while in the cold working tool life is not reduced because of the temperature. So we have clarity over the hot working and the cold working. And the last one is the warm working. The warm working, if you see, if the material is generally, you can say, very brittle, if it is not much, if a material it is rarely used, if a material is brittle in nature especially, and if you directly perform the cold working on such material, there's a possibility it will fracture. So we slightly heat it above the room temperature, you can say about 0.25 of the melting point. We heat it above the room temperature, so just enough to soften the material a bit so that we can perform the metal forming processes. So that is warm working operations. So that's all for the temperature ranges in the metal forming process: the hot working, cold working, and the warm working. Now the next topic of our is the strain rate and the strain rate sensitivity. But before going into that, as I have told you before, what the recrystallization is, that we heat the material, provide enough energy to the atoms so that they can rearrange themselves. So it occurs in hot working. And how do they rearrange themselves? Via the atomic diffusion, that is rearrangement of atoms in crystal lattice to remove the dislocation and defects. So there are some terms which you are not familiar with, and you will get some idea about these terms like defects and the solids, dislocations in the metallurgy subject of materials and metallurgy. So for now you just take recrystallization as that we heat the material, we provide enough energy during that heating that the atoms in that material are able to rearrange themselves, so the effect of strain hardening wear off, you can say, or to remove the effects of strain hardening. Right. Now there is another thing that is called as the isothermal forming. We have discussed hot working in the metal forming processes. What was a hot working? In which we heat the specimen from 50% of its melting point to the 75% of its melting point. So what happens, let's suppose if this is my tool and it is really hot, right, and there's it is undergoing the rolling operation. It is undergoing the rolling operation. Right, and these rolls are compressing this hot material. This is really hot. Let's suppose it is at 700 degrees centigrade, but the tool is at the room temperature, maybe 25 degrees centigrade. Let's say even 70 degrees centigrade, let's say, because of the hotter environment. So because of this sharp temperature gradient between them, there's a rapid heat transfer from the material to the tool. So there are two disadvantages. There are two primary disadvantages of this one. The first thing is it reduces the tool life, as we have studied in the disadvantage of the hot working. The second one, because of the sharp rate of heat transfer, the material or the atoms here rapidly crystallizes. There's a rapid crystallization here, and the fine grained structure starts to form. So the plastic deformation within the same material differs. So the plastic deformation pattern in the different regions of material disturbs. So that is why it is not desirable. So what we do, we also heat the tool up to a certain temperature. If not 700 degrees centigrade, at least let's say 500 degrees centigrade, at least closer to the temperature of the workpiece. So our primary purpose is to reduce the temperature gradient. So we heat the tool also to reduce the temperature gradient, so that the rate of heat transfer also reduces, although it reduces the tool life as well, but plastic deformation occurs smoothly. Now the next topic in this chapter is the strain rate sensitivity. So the next thing we are going to discuss is the strain rate sensitivity, and this comes into play in the case of the hot working. So as we know, in the hot working, the strain hardening is theoretically zero. That means the material is not being strain hardening, so with the strain, the strength of the material is not increasing because it is in a perfectly flowing pattern. So but in the case of the hot working, the additional factor that comes into play is the strain rate sensitivity. That means at what rate the strain is being produced. The strain hardening coefficient, as we know, that becomes zero, so the required stress to deform plastically is gained here. So as we know that the flow stress is equals to K exponent n, and we say in the hot working it becomes zero. That means this becomes 1, so that is equals to the strength of the material, right? So that is equal to the strength coefficient of the material. So that means there is no increase in the flow stress required to produce a further strain, right? There is no incremental flow stress required for producing the plastic deformation. But this is where the strain rate sensitivity comes into play. So at elevated temperature, materials are strain rate sensitive. As we know, in the hot working, we heat the material from 50% of its melting point to the 75% of its melting point. So at this temperature range, these material become sensitive to the strain rate. And at this state, flow stress equation does not work properly. The stress equation we have studied, it doesn't work properly. So as we know, that is equals to Ke power m. So the we reduce this equation of the flow stress to a new equation, that is this one, where this is the strain rate that's equals to V by H, where V is the speed of the tool at which it is producing the strain, and H is the instantaneous height or the length, whatever we are reducing or whatever we are changing. So that the dimension which we are reducing or changing, and the speed of the tool, so that's the strain rate. So the flow stress equation is reduced to YF equals to C, that is the strength coefficient, same like K, but it is measured at strain rate equals to 1. So if the K value is measured at strain rate equals to 1, then that becomes C. It is known as a strength constant, and here M is the strain rate sensitivity. So what is the physical significance of this M? It tells us how much sensitive the material is to strain rate. Okay? This M tells us how much sensitive the material is to the strain rate. So at the higher temperature, the value of M increases, which means at higher temperature generally materials are more sensitive to strain rate, and whereas at the room temperature M equals to 0 at room temperature. So the more complete expression for this one would be combining the original flow stress equation, that was K e power n, and the strain rate sensitive equation, that was YF C into strain rate exponent M. If you combine both of them, we have a new equation that is equals to, as you can see, a combination of K and C, taking into account the strength coefficient as well as the strength constant, into the strain exponent, strain hardening exponent, into the strain rate exponent M, right? So if you see this curve, when the material was being deformed at the room temperature, so there was a strain produced, and the requirement of the flow stress wasn't increasing that much, and it is the case in the hot working. These are all the graph of hot working operation. So in the hot working, when the material was at, let's suppose, a very high temperature, 700 degrees centigrade, and when it was being deformed, it was being deformed smoothly. But as soon as it's at a room temperature, so material was being deformed smoothly. But as soon as we start to increase the temperature here, because of the strain rate sensitivity, although the strain hardening isn't happening theoretically, but due to the strain rate, the requirement of the flow stress increased in the material. So this is termed as a strain rate sensitivity. Although there are many factors, but why do it occurs? There are many factors to it. It depends upon the type of material we are using and several, or the temperature range. So there are several factors to this one. Why does it occur? So for now, this is just a concept I want to deliver, but in the next chapter, this is the end of this chapter, fundamentals of metal forming. In the next chapter, when we will be dealing with the specifically rolling, forging, extrusion, and we will be solving the design problems, we won't be considering the effects of a strain rate. For the sake of simplicity, we will base our calculation on the simple flow stress. So that's all for this chapter. Should you have any question, you may reach me at the Google Classroom. In the next lecture, we are going to discuss chapter number 19, that is the deformation, bulk deformation processes, and in that chapter we will be discussing all those 4 type of bulk deformation processes in details.